Hess's law and heats of formation. So you should be a little bit familiar with Hess's law, and I'm sure you're familiar with heats of formation, so this should mostly be a review, but we are still talking about enthalpy and delta H and types of energy here. So we've been kind of calculating delta H using calorimetry. So essentially that's what we've been solving for in that manner. But there's other ways to calculate delta H, and one of those ways is Hess's law. So as we know, enthalpy is a state function. So remember, a state function, we don't care about the path, we just care about that overall change. So I don't really care how you got from point A to point B, it's just the fact that there was a change from point A to point B. So Hess's law states if a reaction is carried out in a series of steps, delta H for the overall reaction equals the sum of the enthalpy changes for the individual steps. So again, just kind of like we have here, it doesn't really matter the steps that we take. What matters is this kind of overall change that's happening here. That's really what we care about. And you could get that by doing negative 802 plus negative 88. That would get you the negative 890. So again, it doesn't matter if this happened in these two kind of like this 1-2 step or just this one step. You would still get the same delta H value. So this is the problem we're going to look at. We want to calculate delta H for the following reaction. 2 carbon plus H2 yields C2H2. These are the three reactions we have to work with. So, couple things to remember about enthalpy. If you reverse the reaction, you need to flip the sign. If you multiply or divide, you need to also multiply or divide delta H. So those are the main things you want to remember. So what I like to do in these problems is I kind of just want to go through and kind of highlight what we have here. Make sure everything's on the correct side. So we have 2C, where's C? The only place I see a C is here. So okay, that'll be my C. H2. Where is H2? Down here. There's my H2. And my C2H2 is here. It's here. Okay. So those are kind of what I'm concerned with. Everything else over here, we have to hope that that eventually is going to cancel out. If not, we're going to have a problem. So if we look here, you have to make sure that your elements are on the correct side. So our carbon here is on the reactant side. It's on the reactant side here. All right, we're good. Hydrogen's on the reactant side. Hydrogen's on the reactant side. Good. C2H2 is on the product side. Here, it's on the reactant side. So that means we're going to have to flip this first equation. So remember, when I flip the equation, I need to flip the sign of delta H. So delta H now becomes positive. So if you want for yourself, do like a quick little rewrite of the equation. Because sometimes if you just keep staring at it in the same order, you forget that you've flipped it, and that's not good. So we have C2H2 and then 5O2. So we no longer kind of care about this equation that we have here. We really are concerned about the flipped equation. So we don't really care about this one anymore. However, we can still kind of highlight, we got this C2H2 over here. So that's good. That's what we want. Okay, now we have to make sure we have the correct amounts. So let's start from the end this time. C2H2, there's 1 mole. There's 1 mole here. Okay, don't mess with it. 1H2, 1H2. Don't mess with it. Here we have 2 carbons. Here we only have 1 carbon. That means we need to multiply this second equation by 2. So we're going to put a 2 in front of everything. That means we need to multiply this delta H by 2. And when we do that, it now becomes negative 7, 8, 7. So we're kind of not dealing with this anymore. This is our new delta H now that we've doubled everything. All right, so the 3 that we're kind of concerned about are good to go. They have the correct numbers, they're on the correct sides. Lastly, we need to make sure that everything else cancels out. So we have 2 CO2 on this side, 2 on this side. Disappears. 1 H2O here, 1 H2O here. Disappears. Remember, if they appear on both sides of the arrow, they can cancel out. Okay, we have 5 halves O2 on the right side. Left side, we have 2 plus a half, which is 2 1/2, which is 5 halves, so all of our oxygens will cancel. And this is a good way to kind of double check that your answer is correct, because all this other stuff should cancel out. If it doesn't, that means something went wrong, okay? So we have 2C plus H2 left over yields C2H2. This is good, it matches this equation. Our last step is to add everything up over here. So our final answer is positive 226.8 kilojoules. So that would be our final answer. So again, to kind of recall about Hess's law, what you want to do is look at the overall equation you want, find where each of those elements are in however many equations are given to you. Once you find where they are, make sure they are on the correct side of the arrow. So that's why we had to flip it over here, because C2H2 is a product. Then you have to make sure you have the correct molar quantities of all of them. So we were good for the C2H2 and hydrogen, but we had to multiply this by 2 to match the 2 carbon here. As always, make sure if you flipped something, you change the sign. If you multiplied, make sure you multiplied by something here. Add up all your numbers, positive 226.8 kilojoules. So there are many, many different methods to calculate delta H. So far we've used calorimetry, now we've used Hess's law. Now you can also find delta H values on tables. So they'll have there's all different types of enthalpies. There's the enthalpies of vaporization, where you're changing a liquid to a gas. There's enthalpies of fusion, that's when you're melting a solid. You have enthalpies of combustion, when you're combusting a substance and oxygen. You also have enthalpies of reaction. So all these different reactions, they can also have their own enthalpies. So a lot of this stuff has already been tabulated. And the way it's done is through experimental design. So people have done these experiments and then kind of recorded their delta H values. So once they have so many, they can get an average, make sure they're getting really close, they can tabulate these values. But another type of enthalpy we have is another type of enthalpy you could have is an enthalpy of formation, also known as heats of formation. So there's kind of 2 different things you could be referring to. You could have delta HF, which is just the enthalpy of formation. This is the enthalpy change to form a compound from its constituent elements. So it would be like if you were trying to form NaCl, it would just be the heats of formation if you combined Na and Cl to make NaCl. So you're not using any compounds on the reactant sides, you only have elements. Delta HF with the degree sign means something else. So your delta HF here, this has this degree sign. That means it's a standard enthalpy of formation. So that means you're forming exactly 1 mole of a compound. This degree sign stands for standard condition. So standard conditions when we're talking energy is 1 atm and 298 Kelvin. Very important, do not confuse it with the standard temperature and pressure for gases. That is 1 atm and 273 Kelvin. For energy, and when we talk about delta G, and when we talk about equilibrium, it's going to be 298 Kelvin, so just keep that in mind. Delta HF for all elements on their own is 0. So if I said, what's the heat of formation of oxygen? 0. It's in its elemental form. You're not forming it from anything. So if it's already in its elemental form, then the delta HF would be 0. So do the following equations represent delta HF? So remember, delta HF is the formation of 1 mole of a compound from its constituent elements. So let's look at number 1. We have 2Na plus 1/2 O2 yields Na2O. Things to check for. Are we only making 1 mole of product? Yes. Okay. Is it formed from its elements? Yes. So this would represent a delta HF because you're forming only 1 mole of the compound from its constituent elements. So this would be yes. Give it a Y. 2K plus Cl2 yields 2 KCl. This is a no. Why is this a no? Well, you're forming 2 moles of product, so that's not going to work. So no, that would not represent a heat of formation. C6H12O6 breaks down to C6 plus 6C, plus 6H2 plus 3O2. This is also not a heat of formation because you are not forming the C6H12O6. If this reaction were reversed, then yes, it would be a heat of formation. But since it's in this direction, it's not because you're breaking down the compound, you are not forming it. So basically what you want to remember is you're forming 1 mole of a compound from its constituent elements. So we can say the delta H of the reaction is equal to the delta HF of the products minus the delta HF of the reactants. So you can use standard heats of formation to find the standard enthalpy change for any reaction. Very important though, you're doing products minus reactants. You also need to make sure you multiply by the moles of each substance in the reaction. So let's take a look here. So we're going to calculate the enthalpy change for the combustion of C6H6 to CO2 and H2O. So here's our balanced reaction. Now what's important is the heats of formation can be found in a table. So for practice problems in class, I will give you a table. On the AP exam and on any test or quiz I would give in this class, the heat of formation would somehow be given in the problem. So the problem might give you a little mini table with the heats of formation that you need, or maybe somehow you're calculating a heat of formation from other information. So just be aware that when you're doing practice problems in class, I'll give you a table to refer to, but on a test or quiz or on the AP exam, those heats of formation will be given in the problem. So for this problem, remember, we do products minus reactants. So we're going to be doing 12 moles of CO2 plus 6 moles of water minus 2 moles of C6H6 plus 15 moles of oxygen. Now remember, heats of formation for elements are 0, so we're really not going to be using the oxygen in here. So you would have 12 times the CO2. Now make sure when you look this up on a table, it's CO2 gas. The state of matter does matter for this. So we have 12 times negative 393.5 plus the 6H2O, 6 times negative 285.8, and that's the liquid H2O, minus 2 times 48.7, which is the heat of formation of C6H6, plus 0, the heat of formation for oxygen. Substitute that all into your calculator, negative 6534.2 kilojoules. So it's very easy to calculate a delta H from heats of formation because you're really just substituting numbers in. Just make sure you have a balanced reaction. So remember, for Hess's law, if you flip a reaction, flip the sign. If you multiply or divide, make sure you also multiply or divide the delta H value. Then you add them all up. For heats of formation, just be sure that you're using the correct state of matter for whatever reactant or product you're using, and make sure to multiply by the molar quantities.